I'm wondering quite basically how you see black holes as connecting general relativity and quantum theory. And this, of course, brings us back to at Hooft and Hawking, as you mentioned, and how this might lead to some paradoxes.
Well, black holes are the most, well, first of all, symmetric objects that we have in gravity, and they're also the most dense and extreme objects. It's where mass is sort of concentrated in such a small part of space-time that light cannot even escape. I mean, and that means that the matter is so dense that there is a certain region, a certain distance from which light can no longer escape to the viewer outside. And this creates some imaginary sphere around this matter that we call the horizon. So if you are behind that horizon, you cannot get out. And which of course already poses a question. I mean, in normal, the way that Newton describes space and time, every point of space is connected to another point. You can always communicate. But in Einstein's theory, because of the curvature of space-time, suddenly it appears possible that there's a certain part of the space that you cannot send light signals out. And light is, you cannot go faster than light. Light is the most speedy way in which we can communicate with each other. And so if light cannot get out, nothing can get out. And this is why a black hole hides something behind its horizon. And which in a certain way is not satisfactory, because we don't see anything from the outside. When we throw in matter into a black hole, the only thing we see is the mass, because the mass still has a black hole still has a gravitational pull. So we can measure the mass, and if we throw charge into the black hole, we probably can also measure the charge still, and things like the rotation, the angular momentum, we call this, can be measured. But those are the only things we know about. And this was around the time of when Hooft was also working on this description of the standard model. Hawking at the same time was thinking about black holes, and he and others discovered that black holes have certain properties that look very much like what we normally use to describe the laws of thermodynamics. I mean, if you think about gases and fluids with a temperature, they satisfy certain laws that tell you, for instance, that something that has a temperature and an energy, you can have a relationship between them. And this is where the notion of entropy also comes in. There's the first law that tells you that the change in the energy and the change in the entropy are related, and they are proportional actually with the temperature as the proportionality constant. Now, this actually came out also as a law that was discovered for black holes. Black holes, namely, also change their energy if you throw in mass into a black hole. Because of Einstein's equivalence between energy and mass, you're actually increasing the energy. And it turns out there's also an increase of what we call then the entropy. So the entropy in thermodynamics should be thought about as a measure of how much information, of how much microscopic information is necessary to describe a microscopic system. While for a black hole, we don't know what's inside the black hole. It turns out that there's some way that we can still count how much information is inside the black hole, which is this entropy. And that entropy turns out to be proportional to the area of its horizon. This is what Hawking discovered together with Bekenstein in the 70s. And in order to derive that, actually, he made use of quantum mechanics. So it's a property of quantum mechanics that turns out indeed that these black holes have a temperature, because that was what Hawking then showed. The idea of the entropy was actually due to Bekenstein, but Hawking indeed showed that black holes do have a temperature, and that quantum mechanics namely allows you to see a certain kind of radiation, sort of like a hot object is emitting radiation, and black holes also radiate with a certain temperature that was calculated by Hawking. And together, when you put the temperature together with this entropy, you have then a relationship between the change in the mass and the change in the entropy. That's exactly this first law, this law of thermodynamics. So this was a very deep discovery. And I think it's one of the biggest discovery that was made in the last century. I mean, I really think that it was the way in which eventually we're going to be understanding the relationship between gravity and quantum mechanics. Although at that time we had no idea what that entropy meant. I mean, I mentioned that this entropy can only be, well, explained if you know how to describe what's inside this black hole in a microscopic way, because the entropy represents in how many ways you can represent a microscopic object. I mean, if you think about the entropy of a volume of where gas of particles are inside, it's actually counting all the possible ways that these different particles can orient themselves or how they can move and their velocities. If you know where they are, if you keep that all, put that all together, you get an enormous amount of information that somehow is then counted by this entropy. And very loosely speaking, I mean, the way you can think about this entropy is that if I would write down all the positions and the velocities, I would write them down in some numbers. I have to put this in some database with all kinds of bits. And those bits we count as zeros and ones. And if you know how many bits I need to describe all these positions and velocities, that number of bits you can think about as being the entropy. And so we needed something similar for black holes in order to explain what is the origin of this entropy. And at the time, and certainly when at Hooft started thinking about black holes, we had very little knowledge about this and very little tools even to address that. And this is where string theory eventually, I think, came in, and why indeed bringing together string theory and the study of black holes is sort of such a promising field, because it's somehow this question about what is the entropy of a black hole, and the way that string theory eventually provided us with an answer, is how we now are making progress and how we now are trying to answer the questions that were already posed, say, almost 50 years ago.